This example is supposed to illustrate the difference between horizontal shift and phase difference. In the upper picture, there's a graph of f of theta equals sine theta. And there's also a horizontal shift of the function. And it's a shift to the left. So which function is which? The blue function is the original sine theta. The red function is the shifted function, sine of theta plus pi over 2. When you add a constant directly to the variable, what that does is it actually shifts to the left. It's the opposite of what you'd expect sometimes. And if you subtract a constant from the variable, you're actually going to be shifting it to the right. So I'm going to give some symbols that can stand for that pi over 2 quantity. It'll be omega h. In that upper problem, omega h is negative pi over 2. Now, how do I know that? Well, the general form here says that we're going to have omega theta minus omega h. But we don't have a minus in our formula. We have a plus. But the only way we can get a plus is if our omega h is negative. Now let's check out the function in example B. One of these functions is sine of 1/2 theta. And another one is sine of 1/2 theta plus pi over 2. So there's another shift. Which is which? Well, the green is sine of 1/2 theta. The yellow is sine of 1/2 theta plus pi over 2. As you can see, even though we added the same constant to both the top and bottom examples here, the horizontal shift was not the same. And so for this example B, we again want our function in the form of sine of omega theta minus omega h. And that would mean that our omega h is once again negative pi over 2. So both A and B have the same omega h quantity. And that quantity is actually an important quantity called the phase difference. And it is often given the letter phi, Greek letter. And it's the same for both A and B. Okay, so what is this quantity used for? Why is it important in periodic functions? Well, even though both these functions have not shifted the same horizontal amount, like for example, this guy was in a phase of pi over 2 at the current time, and it shifted by 1/4 of a cycle. But that guy is also in a phase of pi over 2 when it comes to the sine curve. 1/4 of a cycle has been completed. And so how much does this shift? It also shifts by pi over 2. So they have the same phase difference. The horizontal shifts are not equal. So B is shifted horizontally 2 times as far. So does the quantity h equals negative pi over 2 really represent the amount of horizontal shift in both situations? No. Does the quantity omega h in the formula actually represent a horizontal shift? No. In what special cases could omega h actually represent the horizontal shift? If, and only if, omega equals 1. In the top picture, that's the case. See, here we're at a pi over 2 angle, and the quantity here is negative pi over 2, and our horizontal shift actually was pi over 2 to the left. And that's only because the omega there was 1. Here, because the omega wasn't 1, it has the effect of exaggerating the horizontal shift that took place. So how can we actually use the quantity omega h to find the horizontal shift of a function? We want to start with the formula for phase difference, which is this. That is the phase difference formula. And so we want to solve it for h. And we'll get h equals phi over omega. Now, how do the phase differences in A and B compare? They're actually the same. Both of them are negative pi over 2. We shifted to the left of 1/4 cycle in both cases. So does pi over 2 represent the phase difference in both situations? Well, it's technically negative pi over 2, but yes. Well, negative pi over 2 represents the phase difference for both. So in general, does the quantity phi equals omega h in the formula represent a phase difference? Yes, it does.